Totally walk up in front of the entire class and be gone for 20 minutes.
All right, so on Wednesday, we started working on the simplex method. And we got through one iteration of the simplex method. I'm going to write it up here real quick. I know I've already used a little bit of time trying to get our equation and our graph up here. But I want to make sure that we're all on the same page. So remember, we have an equation with now 5 variables in it instead of just 3, right? Or 2. Instead of just x and y, we have our slash variables here. And if we look at the coefficients of our objective function, we have entered them as that first line right there. And what we said is we're going to do something really silly, and we're just going to assume, to start off, that x and y are equal to 0. Because what that's going to allow us to do then is get an equation not with 5 unknowns in it, but an equation with 3 unknowns. And at first it's super easy. If x and y are both 0, we already have the solution for S1, S2, and S3. So we're just going to do that. S1, S2, and S3 are going to be here. And what we did is we said this is the basis, this is the coefficient of the basis across the top, and we copy the pertinent value from here to here because it's going to be easy. So S1 is 0, S2 is 0, and S3 is 0. And then this is going to represent these equations over here. We're just going to take the coefficients because we know what the variables are. Those are the column headings. And we know we're adding them together to get this right side here. So I'm going to do that very quickly. And our right-hand sides were 8, 10, and 8. So then we have our ZJ and CJ minus ZJ. I want to make sure I explain ZJ well. I think I may have confused you without you knowing it because we haven't done the second iteration. The way that we get this row right here is we multiply these values right here by the corresponding column above it. So, and then we add all those two together. We're doing a dot product is what this is called. So 0 times 2 is 0, and we add that together with a 0 times 2, and we get 0, and a 0 times 1 is going to be 0. And as you can quickly see, because we're multiplying everything in here by zeros, that this entire row right here is going to be zeros. All right? Then the way we get this row is we subtract this row, we subtract this z sub j row from this row right here. So 3 minus 0 is 0, 4 minus 0 is 4, and then 0 minus 0 is 0. Hopefully this is a good review. Then the value here we said is the current value of our objective function. So the current value of our objective function is 3 times x. What's our current estimate of what x is? So that contributes 0 to our objective function. Plus 4 times y. And what's the current value of our... It's 0, so we add another 0 to our objective function. And even though we have values for S1, S2, and S3, because they're implicitly zeros, our total for our objective function remains 0 to begin with. Notice that the values over here represent the current values of these variables. And that's because these values right here are 0, and the only other non-zero value is S1 in this row. So S1 has to equal 8. These two values are 0, so the only other one is S2. So S2 is 10, and S3 is 8 here. So we always are going to know what our current guess for our values is by just looking at these variables here and assigning them to these values over here. Alright? Finally, this is our last little bit of review. We said that these numbers right here represent how much, if we're going to change our guess from x and y, we're going to move along the y-axis, or we're going to move along the x-axis here, how much we have to reduce one of these variables by to keep this equation in balance. So we said, for instance, that this 2 right here represents that if we increase y by 1, we're going to have to decrease S2 by 2. Right? So let's look at that equation right there. That is 2x plus 2y plus S2 equals 10. Right now, our current guess is that x is 0, and y is 0, and S2 then has to be 10. But if we change this y from 0 to 1, we increase it by 1, we've added 2 to this left-hand side. That's what that 2 says. The only way we can keep that balance is we have to subtract 2 from here to keep it in balance. And that was what led us to be able to decide how much we could increase or decrease one of the values that we put in here. Now we looked at these two values. Which one did we say we were going to use? We were going to use the 4. Why? It allows us to make the biggest step towards our optimum solution. So we know we're going to insert y into a new solution here. So I'm just going to go here because we're going to do another iteration here. Below that, we're going to have S1, S2, and S3, or S3. One of those three is going to come out and it's going to be replaced by y. And what we did is we divided each one of these numbers right here by this, because this tells us how much we have available to do. S1 is currently 8. We could increase y all the way up by 8. 8 divided by 1. That's how much we could. And we said that that represented this point right here. We could raise it up to 8. Whereas here, we can only do 10 divided by 2. Because we have 10 units available, but every step of y goes 2 in that. And so that represents this point right here. And then finally, we said that this, we had 8 steps, but each one takes 2 out of S3. So we can only move it up by 4. And so that's what we said we were going to do. We're going to move to now this point. And so we're going to get rid of S3 because it is the lowest value. It's the most we can move it without going outside of our feasible region. It prevents us from moving more, to 5 or to 8, because if we move past that, we would go outside of our feasible region. So this is going to be the variable that is going to end up having a 0 value. It's going to have no more slack, and we're going to insert y in its place. So we'll do this, S1, S2, and y here. And this is where we left off on Wednesday. Now we can do the same thing that we did here for this column here. We're going to take the appropriate coefficient and copy it down here. So what value should go here by S1?
0.
It should be 0. What should be by S2? And what should be by y? 4. Okay? And now, what we want to have happen is we want Before, we said it was really important that we had 1, 0, 0, 0, 1, 0, and 0, 0, 0, which were associated with each of these values that were in the basis. But we've changed which values are in the basis. So what we want is S1 is going to remain the same. We're going to want a 1, 0, 0 here. S2 is not changed, so we're going to want a 0, 1, 0 here, just like we had before. But now, Y is taking S3's place. So we want to have 0, 0, 1 in this column because Y is one of our values, not S3. Okay? So remember, each of these lines are part of these equations. So if we had a 2 here, and we want to make it a 1, what mathematical operation do we have to do to transform this 2 down to a 1? We have to divide by 2. We have only the 2 operations that we talked about when we were solving linear equations. We can multiply by a fixed constant, or we can add 2 equations together. So we're going to multiply this entire equation by 1/2, so that we can turn this into a 1. So 1 times 1/2 becomes 1/2. 2 times 1/2 becomes a 1. Fortunately, 0 times 1/2 stays 0. 0 times 1/2 stays 0. And this 1 becomes a 1/2 right here. Okay? This is the same set of steps, equivalent set of steps that we were doing when we had systems of linear equations, except we're hiding a lot of the extra letters and numbers associated with it. Now, we need to get these zeros in place right here. We had it. Let's go for this 1 right here. We want to transform it from a 1 to a 0. So what we're going to do is we're going to take this equation right here, and we're going to subtract this equation from it. Because 1 minus 1 will get us this 0 right here. Alright? So we're going to take this equation and subtract this equation from it. So what's 2 minus 1/2? 1 minus 1 gets us our 0. 1 minus 0 gets us our 1. 0 minus 0 gets us our 0. And 0 minus 1/2 minus 1/2. And we already knew a problem here. I need to do the right-hand side of the equation. We can't just manipulate half the equation, we have to manipulate the whole. So what goes right here? Back up a little bit. 4, because we do the 8 divided by 2 and get the 4. Now we can do 8 minus 4 to get 4 here. Alright, let's get this last row in place. We want to get this as a 0 here. How can we get this 0 here? Yeah, we can subtract and do our zj, and then our cj minus zj. Okay? Someone help me out. How do we compute the zj? What do we do? No, we don't plug it into our objective function. That's what we put over here.
Multiply the CB column, then add together all the different, like the X column, add all those.
Yes. We're going to multiply each element of these columns together and add those results. So 0 times 3/2 gets us 0. Added to 0 plus 1 gets us, added 4 times 1/2, which gives us 2. Okay? We do the same thing here. We got 0 times 0, 0 times 0, and 4 times 1. Okay? 0 times 1 is going to get 0. 0 times 0 is going to get 0. And 4 times 0 is going to get 0. Again, 0 times 0, 0 times 1, and 4 times 0 is going to get us 0. Now let's look at this. 0 times negative 1/2, 0 times -1, and 4 times 1/2 is 2. Now this is where we plug in our value of our objective function. Okay? So our objective function, 3 times, what's our current value of x?
2.
Our current value of x is 0, so this is going to give us 0. 4 times our current value of y, which is 4, so a total of 16, and then we multiply 0 times everything else. So the current value of our objective function at this guess, let me put this in a different color here, our value of our objective function here was 0. Our value of our objective function here has raised up to 16. So that's good. We have improved our objective function so far.
So if you did the same thing that you did with all the columns to that last column, you would get 16. Is that an way to do it?
Yes,
Okay. Why?
because you're multiplying the value on the coefficient, and these are all the non-zero values. So these will always be 0 for slack and surplus variables, and they'll be non-zero for actual variables that you care about. So yes, that will work if you multiply this column times this column to get that. Okay, CJ minus CJ. We're going to subtract this top line right here. This top ZJ from it. So what's 3 minus 2?
1.
What is 4 minus 4?
0.
0 minus 0? 0 minus 0?
0.
And 0 minus 2.
-2.
Yeah, I knew how it got these, but I didn't know how to.
All right. What is now
Somehow get
our highest value in that line? So now, what we're going to do is we're going to add x into our basis, which means that we're going to move out on the xward round. But we're not going to move perpendicularly, right? We have to stay within our feasible region. Where visually, where do you think we should land at our next guess? We better land all the way down here. Right? Because that's the next important possible answer to our solution. So we want to move outward in the x direction. It's actually going to drop us a little bit in the y direction towards this point. We know that by increasing x, we're going to increase the objective function somehow. Okay? But it's probably not going to be as much as when we increased the y. Okay? So now we're going to repeat this process all over again. We have to figure out which variable we're going to replace x, which variable x is going to replace. Okay, so how did we decide which variable y replaced up here? Not the lowest right-hand side. We had to do one quick arithmetic operation first, right? We had to divide it by the column of the variable that we were using to replace. So now we're going to divide by these values right here, because we're replacing with x instead of y. So what is 4 divided by 3/2? 4 divided by 3/2, remember your is the same as 4 times 2/3. Right? So that's going to be 8/3 right here. This one's easier. 2 divided by 1
2.
is 2. Thank you. And 4 divided by 1/2
8.
is 8. Okay, so which one is the smallest value here? The 2 is, right? Because 8/3 is 2 and 2/3. Right? So that means which variable is x going to replace? S2. Okay, so if you've got long enough paper, you can make another row underneath it. I have run out of whiteboard, so I'm going to come over here. X. Wow, let's go a little tiny bit. X, Y, S1, S2, S3. Alright. goes here, 3, 4, 0. So now we keep S1, but we replace S2 with X, and we keep Y. Okay, what goes right here, in these spots right here? We copy the 0 from there, we copy the 3 from here, and we copy the 4 right there. Okay, so now X right here is going to become, it's going to have the same characteristic that S2 did, right? We're going to want the column for X to look like S2's column did. So that means X better look like this, 0, 1, 0. S1's column should stay the same, and Y's column should stay the same. Right here. Because those are in our basis. Those are our non-zero values. So we need to transform our equations from this, where X had these fractional values, to this, where it's 0, 1, 0. And notice that we still have that same pattern, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, that is essential to the correct solution to our equations here. So how do we get this 1 here first? What are we going to do? We already have it, right? It was a 1, so we don't have to do anything special there. So we just preserve that row. 1, negative 1, and 2. We already had this 1 here. Now how are we going to turn this 3 halves into a 0 here? What do we have to do? Yeah?
Multiply the bottom equation by 3 and subtract.
Okay, so we can multiply this by 3 and subtract. We don't want to do that though. Because if we do that, we're going to introduce a non-zero value into here. So we have to use this equation because we want to keep this a 0. Okay? So we're going to have to multiply this one by negative 3 halves. Okay, so multiply this equation by negative 3 halves, and then we can add it together. That will keep this a 0 right here. Alright, so negative 3 halves plus positive 3 halves gives us our 0 that we want. Negative 3 halves times 0 plus 0 keeps us in that 0 range. Negative 3 halves times 0 plus the 1 keeps that 1 here. And now we can go. Negative 3 halves plus 0 gives us negative 3 halves, right? And then finally, negative 3 halves times negative 1 gets us positive 3 halves. We add positive 3 halves to negative 1 half, and we get positive 1, right? And then negative 3 halves times 2 gives us negative 3. Negative 3 plus positive 4 gives us positive 1. Alright? Is everyone following me? Now let's do this last line. We want to turn this 1 half into a 0. Yes?
I'm sorry, why is the S1 column and S2 row negative 3 halves when there's a 0 both times?
Right here? Because we multiplied this whole row times negative 3 halves and added it to this whole row here. So although it had a 0 in here,
Because
the one below had a 1, it turned it from a 0 to a negative 3 halves. Okay, what are we going to do to turn this into a 0? We have to use this equation. So we have to multiply this by -1/2 so that we can add it to here and get it to 0. So -1/2 plus +1/2 gets us our 0. -1/2 times 0 keeps us 1. -1/2 plus 0 times 0 keeps us 0. -1/2 times the 1 gets our -1/2. We add that to 0, and that's going to give us -1/2. -1/2 times -1 is going to give us +1/2. We add that to another +1/2. We're going to end up with 1. -1/2 times 2 gets us -1. We add that to 4, and that gets us 3. Okay, so what is our current guess for what x and y should be? What's this point right here? 2, 3, right? X equals 2, and that lines up pretty good graphically. And y equals 3. That lines up pretty good graphically. Okay? So that's our current guess. We're not done, however, because maybe this is the optimal point. Right? So let's keep going.
So you need the graph.
No, I'm showing you how this traverses the graph to connect the visual intuition that we've been doing so far with the mechanism that we're doing.
How do we know?
That's a great question. How do we know when we're done? Well, let's see here. Let's compute these rows. Okay? How do we compute this row, this z sub j row here? We multiply these 3 numbers times each element of these columns and sum them up, right? So what's 0 times 0?
0.
Plus 3 times 1?
3.
Plus 4 times 0? 0 for a total of 3. Okay? 0 times 0, 3 times 0, 4 times 1. 0 times 1, 3 times 0, 4 times 0. 0 times -3/2, 1 times 1, 1. 4 times
Is that 3 times 1?
3, oh, sorry, I can't multiply, thank you. I went through the wrong column here. 3 times 1 is 3, and 4 times -1/2, -2, for a total of +1. 0 times 1, 3 times -3, -3, plus 4 times 1, yeah, you're going faster than I am. 4 times 1, so -3 plus 4 gives us +1. 0 times 1, 3 times 2, 6, plus 4 times 3, 12, so 6 plus 12 is 18. We're going to put that right there. We have seen, like we predicted, an improvement of our objective function now up to 18 right here. Okay? Let's do our last line, c sub j minus z sub j. So 3 minus 3 gets us 4 minus 4, 0 minus 0, 0 minus 1, and 0 minus 1. Okay? These, being 0, mean if we were to switch these out, well, you can't switch them out because they're already in. You can't switch them in for something when they're already in. But if we were to substitute one of those 3 with either one of these 2, instead of improving the objective function like we did here, or like we did here, if we put either S2 or S3 back in, it would actually cause a decrease in the objective function because they are negative. Okay? And so as soon as we get to the point where we have non-positive values here, we know that we're done. We're done. Yay! So this is a 3 steps in the process. We introduced, we did it with our first guess to decide that we put y in, to decide that we put x in, to decide that we're done.
Absolutely.
So the optimum solution for this problem is that x equals 2, y equals 3, our first slack variable is 1, and our other 2 don't have slack because we're binding. Alright? Yes?
I know it doesn't matter what, but the S3 column,
Uh-huh.
the number 1 at the top, should that be a -1?
Well, the way we got it is we multiplied,
-3 halves.
we mod -3 halves
Times -1,
times negative, which gives you positive 3 halves.
and then times the.
No, plus. Positive 3 halves minus 1 half gives us 2 halves. Positive 2 halves.
Okay, I thought it was like that.
Yeah, no, we added this together. Okay? So this is our maximization problem, okay? This is the routine that you have to go through for maximization problems here, okay? But what happens if we have a minimization problem? Wait, actually, minimization problems turn out to be not too difficult. Okay, so let me give an example here. Well, let me say this. Minimization problems aren't any more difficult than that.
Yeah, that's
Just like not difficult or difficult.
I would say it's tedious. I don't think it's difficult, but it's tedious. Yes. Hey, listen up. Anna wants to ask a question.
So over here, the C sub D at the top
Uh-huh.
is the same as C sub J minus C sub J the first time,
Yes,
but not the second time.
right.
Then you go back. You said we could just keep going.
No, well,
down if we wanted.
we always went back to this.
Okay.
Yeah, so we didn't subtract this. We didn't do 3 minus 2 to get 1 and 4 minus 4. We did this 3 minus 2. It just happened to be that these were the same value.
All right, thank you.
Yes,
So is this like what the Excel formula does for us, and we're
Yeah.
learning what the Excel formula is actually doing?
yes, yes. That's exactly what's going on.
Good question.
Yes,
So if, like, for this example, this has 3 slacks, and is that why we did the steps like 3 times through, like the thing 3 times through? Because on our homework, it's like 2 of them, so it would be like only 2 times through.
no, you have to go until you get negative values.
Yeah, but like,
It could be that you have more steps than slack variables,
Okay.
yes. Because you might, because of the shape of the thing, you might attempt to put 1 slack in, then take it out, and then put it back in to the solution. So you can't predict how many steps there are gonna be based on how many slack or surplus variables there are. So you have to go until this happens. Sorry. Alright, so let me give an example, minimization problem. 360x plus 120y,
do that yourself.
subject to
How do we have enough room?
X
Minimization.
plus y is less than or equal to 8. And 2x plus y is less than or equal to 10. And y is greater than or equal to 4. X and y are not negative.
I'm not gonna be able to read the board.
Alright, the first thing that we do is we add in our slack variables, right? So these are all less than, well, these two are less than or equal, right? So we would do S1 and S2, and here we would do S3 minus. And now here is here's what we do for minimization problems. We don't ever solve minimization problems, we only solve maximization problems. So we're going to transform this minimization problem into a maximization problem, and then we'll use the same steps we used before. Okay? So here's what we do. Yes?
Why?
Because then we only have one. Because then we only have one set of steps to follow. Okay? So it's so that we always treat everything the same. And the way we do that the way listen. See, that's easy. So for the minimization problem, we wanted low values of x, right? And low values of y. That's what would give us a minimum. So if we want to get a maximum value, what we do is we negate our objective function. All right? So if we get a super close to zero value, that's going to be the maximum value we can get. And then when we invert it, it's going to be the lowest value we could get. If we got, right, this is the minimization value. If we think over time, the different iterations that we're trying, we had some high value, and it got lower, and it got lower, and it got lower. If we do 1 minus that, or negative that, it's going to look like this. Just like that. That's what doing the negative to that is. We just flip it over the x-axis, and we want to get this as close to 0 as we possibly can. And that's going to effectively get us something as close to 0 for our minimization that we wanted. Alright? Yeah. Yeah, well, so the Excel has, you tell it whether you want it to minimize or maximize, and it will, when it does minimize, it will do that. Yes. That's what the computer does as well. Okay? All right. That's all you need to know about minimization problems. Okay, so because of that, well, we're doing the simplex method we're going to focus on maximization problems. So open your books to, oh, you can't because it's chapter 17, sorry. If you've got your computer with you and you've got chapter 17 loaded on it.
Listen to what you just said. Listen to what you just said.
You can look this up. And I've got the equation here. We're going to do 17.3. Because we're not actually done with maximization problems. I just carefully constructed a problem that we could be done with. But now I'm going to reintroduce an issue that we can run into. So if you look at 17.3, you'll see that it says we're going to maximize 5x plus 9y, subject to 1/2 x plus 1y is less than or equal to 8. 1x plus 1y is greater than or equal to 10. And 1/4 x plus 3/2 y is greater than or equal to 6. And our logical constraints here. Okay? So we can insert in our slack variable here, but we're going to have surplus variables for the last two constraints. And how does the sign change for slack? It becomes negative, right? So you guys remember that? Okay? So everything up till now looks great. But I want you to think about the solution that we did with the first problem. What did we do? What was our first guess?
0, 0.
It was that x and y are 0, 0. Let's draw this graph, and we're going to see what the problem is.
Oh,
Okay, so x and y here. So let's do the first one. If x is 0, then y is going to be 8, right? And if y is 0, x is going to be 16. So I'm going to do this as 2. 2, 4, 6, 8. Alright. So the next one. 2, 4, 6, 8, 10. Wait, that's not right.
It should be 16 on the bottom.
12, 14, 16. All right. We're here, right? Greater than or equal, and it's less than or equal here. And then our last one, what's that going to be? I don't even need to draw it to show you what I'm going to do. Our feasible region already excludes 0, 0, right? Before I even draw that third one, our feasible region is right here, right? So making a guess of here is a terrible guess. It's an illegal guess.
Let's do that.
Right?
It seems easy.
So, what we're going to do is we're going to add a fourth variable to our equation here. Space here. That's an A. Right. That A stands for artificial. Okay? And the problem is that S1, if we didn't have S3 here, and we assumed that X and Y were 0, we would get the temporary solution of S1 is 8, and S2 is 10, and, S2 is negative 10, and S3 is negative 6, which violates our logical constraints here. We can't let S2 be negative 10, and we can't let S3 be negative 6. Our solver breaks if we do those negative values. And so they have to be non-negative. So we're going to add a third one in here that we're going to temporarily use to get us a guess that will hopefully, even though x equals y is illegal for this, for our original equation, because we added a3 in here, oh wait, I should have added in a2. Because I've added these artificial variables in here, I can get a solution to this equation, which is a slightly different model than to this model. I should change this. Now what do we want? How do we make sure that our solution to this model matches the solution to our final model? What do we want to be true about these artificial variables here? We want to make them 0. Any suggestions how we can make A2 and A3 turn 0? What if we subtract a really, really big number as a multiple of those artificial variables? The only way we're going to get a good maximum here is if A2 and A3 are 0. If A2 and our A3 are non-zero, we're going to have a really small number. And it's not going to give us a solution. So we're going to create an artificial model based on our original model by adding these 2 extra parameters here that allow us now to have x and y equal to 0 and not break our model. Because we have no clue where x and y should be in here. We have no good starting point. So since we have no good starting point, we temporarily change our model to allow x and y to be okay. And we just force these variables that we added to the solution to end up with 0. So the solution for our alternative equation matches the solution for our original equation. And so because of that, solving this equation is going to be the same as solving our original equation, and we have a known point that we can start with and start out being legal. Alright? We'll follow this through on Monday with the actual simplex method. I'm sorry I didn't answer your question.